Hey, what's up? I'm Dave Boyer, aka Mr. Boyer, aka the Swamp Man, here in my classroom in Kernersville Middle School. I'm continuing my lesson on convergent plate boundaries. So in the previous video, you should have been able to complete that top third of your notes and understand that a convergent plate boundary is where two or more plates are coming together. So we talked about the action involved there with the plates coming together. The cause of it was in the previous video as well, convection currents that are happening inside the mantle and driving those tectonic plates of the crust. So the last part of this, the bottom 2/3 of our notes, are going to be about the result of the interactions of these plates. So I'm going to go back over to the Promethean board and kind of get that bottom section of notes set up. So the top of that paper, and you have to write this kind of small, we got a lot to fit in this bottom 2/3 of our paper, but the top there, we need a statement. So with convergent plate boundaries, the type of plates that are involved make a huge difference. So we wrote at the top that the result will depend on the type of plates involved. So that should tell you that there are more than one type of plate. The crust is made up of primarily two types of plates. We have continental plates and oceanic plates. So we're going to go ahead and kind of describe some of that because that's going to play an important role in the interaction with these and what result comes from it. So I don't think this is actually all that hard to understand. We have continental plates. Continental plates hold up continents. Something else that's important to know about continental plates is that they are also less dense than oceanic plates, and that's going to play a big role in the result, as we're going to see a little bit later. So the other type of plate we have is oceanic plates. And not too difficult to understand this either. Oceanic plates holds up oceans. And oceanic plates are more dense than continental plates. So there's our two types of plates. We can have combinations of those plates that are crashing into each other. We could have continental plates crashing into continental plates. We could have continental plates crashing into oceanic plates. We could even have an oceanic plate crashing into another oceanic plate. So any combination of these is going to give us different results. Let's take a look at our map real quick. So on the map of all the plates that are around, some of it can be pretty easy to understand which ones are going to be continental plates and which ones will be oceanic plates. The Pacific plate is the biggest of the oceanic plates. We have continental plates like the South American plate. The west side of South America, South American plate has that continent on it, the continental plate there. The African plate is going to be largely a continental plate. Two others that we're going to look at, the Indian plate has the subcontinent of India, so it is continental, and it's crashing into the Eurasian plate. We're going to look at that one in just a second. And then later in the lesson, we're going to look at the Nazca plate. The Nazca plate is a piece of the Pacific Ocean, but it's its own separate plate, and it is crashing together with the South American plate. So let's go back to our notes. We're going to look at two different situations. So with the rest of your paper, you can draw a line that goes down to divide it into a left side and a right side. And then we're going to go ahead and set up some drawings and descriptions over there. So the first situation we're going to look at is a continental plate moving into a continental plate. And then on the right side, we're going to be looking at a continental plate crashing into an oceanic plate. And we'll use those two specific examples that I was just going over. So continental crashing into a continental plate is an example of that. Can be the Indian plate crashing into the Eurasian plate. And then over here we can have the South American plate crashing into the Nazca plate as our example there. So we're going to come back to this idea of density. Continental plates are less dense, oceanic plates are more dense. If two things are interacting with each other and one of them has a different density than the other one, then the thing that has the more dense, the more higher density, is going to sink below the thing that is less dense. So that's going to definitely play a role here in this example with continental crashing into oceanic. But if we have two plates of relatively equal densities, one continental plate crashing into another continental plate, I think of that as like two huge sumo wrestlers, and they go running at each other, they boom their big bellies right against each other, and they just keep pushing on each other. Neither of them falls down, they're just kind of holding each other and pushing and wrestling, but neither one is able to win. Whereas in a continental and oceanic plate, that's like, you know, a tiny sixth grader going against a big sumo wrestler. They're going to run up, they're going to slam into it, but then that little sixth grader is going to get flattened on the ground. That is kind of an analogy of what's going to happen over here. So let's look at this continental to continental plate boundary. So I'm going to try to put the camera down. Hopefully you can still see me. All right, so I've got this foam model to represent this. I'm not going to cut it in half, but if you pretend like this foam has been cut in half here, and I'm going to press the two plates against each other. So if they have equal density, then neither one is going to go underneath the other one. And as they push, it's like this equal pushing of forces between them. Oops, sorry. So as they push, they're going to keep pushing up higher and higher and higher, but the forces of the plates are going to continue to push them together even as they get pushed higher and higher and higher. What kind of a physical structure, what kind of a geographical feature do you think this might look like? Looks to me like we got some mountains forming. And there's a particular type of mountain called a folded mountain. You can see the folds in the mountain as they get pushed together. One of the best examples of this, or the example that we're going to use, go ahead and pick up the camera again. One of the best examples that we're going to use is the Indian plate crashing into the Eurasian plate. So let's go ahead and label that. The Indian plate and the Eurasian plate. So I'm going to try to draw that a little bit. First step we have is our two plates. And we should know that they are pushing against each other. They're coming together since it's convergent plate boundaries. Convergent means come together. But since they are equal densities, neither one can really win in that battle. So that's our first drawing, and that's going to lead us down to trying to kind of draw it like that foam pieces that I was just showing you, and the other plate gets folded up also. So there we have our two plates coming together, crashing together, pushing equally on each other because they are of equal density, being continental into continental, and the ultimate result of this is going to be the formation of huge mountain ranges. Some of the biggest mountains on the planet are made in this form, where you have convergent plate boundaries between a continental and a continental plate. So trying to keep our notes consistent, somewhere over here on the left, which I kind of left off, is the result. And the bottom 2/3 of our paper of notes is for the result. So we got Himalayan Mountains as an example, the Indian plate crashing into the Eurasian plate. I'm going to post this video that I'm about to play on my Power School page for you to watch when it's not through this same video. But I just wanted to play it really quickly on the video as well. So this is a time-lapse animation showing 70 million years of movement of the Indian plate, which is the plate here on the bottom left, coming up on the Eurasian plate on the top right. If you notice before the video, or as the video is first starting, there was an ocean between them. The Indian plate actually broke off of the continent of Africa and has been moving to the northwest. When it slams together with the Eurasian plate, their continental plate into continental plate, and we're going to have equal densities, and we're going to start to see that the land around both sides of the boundary are going to be pushed up higher and higher and higher to form these mountains. The Himalayas are the tallest mountains in the world, including Mount Everest, which is credited as being the highest mountain above sea level. Now this process happens over millions of years. We're not seeing mountains that are new mountains that are forming in the Himalayas, but this process hasn't stopped during our lifetime. That continues to work, and the Himalayas are actually growing taller as it works. Some evidence of this happening, often students are somewhat skeptical of things that we learn in class when it's so hard to imagine something like a giant piece of land crashing into another giant piece of land. But people that have climbed Mount Everest, some of them, a couple of geologists, have brought down rock samples from the summit of Mount Everest and from different parts heading down the mountain. And when they analyzed those rock samples, they found that some of them contained fossils of aquatic organisms, of organisms that evolved in the seas. So that area between the Eurasian plate and the Indian plate that was once an ocean was now squeezed together with the land, removing the water between them and pushing that rock higher and higher and higher. And some of those fossils that remained inside those rocks can be found almost 30,000 feet up on the top of Mount Everest. It's really cool stuff. So like I said, I'm going to post this video so that you can watch it without me talking through it down below in the Power School page. So if we go back to our notes, we're going to now transition to another type of interaction at a convergent boundary between a continental plate and an oceanic plate. So our example here, we're going to have the South American plate. South American plate, South America is a continent, so we got continental plate there, and the Nazca plate. Nazca plate just off the western coast of South America, but the Nazca plate is oceanic. So if we remember back, oceanic means that they are more dense. The rocks that make up oceanic crust are more dense than continental plates. Continental plates being less dense. So go ahead and let's draw in that action between them. We're going to have our continental plate here, and it's going to be moving to the right, and it's going to be crashing together with an oceanic plate. That oceanic plate's being pulled by the convection in the mantle at the other plate. So we have convergent plate boundaries. But instead of having this equal match between equal densities, since oceanic plates are more dense plates are going to sink below less dense plates. So let's go ahead and draw in the next transition of those. So the less dense plate is going to float on top of the more dense plate. Oceanic is more dense. This oceanic plate is going to start to be pulled underneath that continental plate. Well, what's down underneath this crust? We've already looked at that with the convection currents in the mantle, right? We got the mantle, liquid rock, a really hot area. So as this oceanic plate is pulled down underneath the continental plate, this leading edge of the oceanic plate is going down into liquid rock, into magma. It's going to get heated up and it's going to start to melt into liquid rock also, creating more magma down in this area. Well, that more rock that's being added there is going to increase the pressure in that area. If we increase the pressure, that fluid is going to have to move from higher pressure to lower pressure. So it might be able to spread out, but if we're adding rock there, it can't keep spreading out. That area is already filled up. So what's really going to happen is that it's going to start to release some of the carbon gases that were in these rocks and releasing some of that pressure upwards. And it's going to find a way to shoot its way up out of the crust. And now we have lava coming up, liquid rock on the surface. So the main result of oceanic crust going underneath continental crust is the formation of volcanic mountains. So this process where an oceanic plate is going underneath a continental plate is the process called subduction. And you're going to have an assignment to do about subduction after you watch this video. Kind of started the video talking about prefixes. The prefix con means come together. This prefix sub means under. Subduction means one plate goes under another plate. A submarine goes underneath the surface of the ocean. Sub means under. So subduction zones are where oceanic plates are meeting continental plates. The oceanic plate being more dense is going to sink down underneath the continental plate. It's going to melt into liquid rock, increasing the pressure there. That pressure has to be released somehow, and the easiest way to release pressure between these two interacting plates is to push that lava up out through the crust and form a volcanic mountain. Pretty cool things. These surfaces are, these plate boundaries are some of the coolest things on the planet, but I just thought I'd stop and share it with you and tell you that science rocks. Peace.